last time we talked about infinite integrals, where we had infinity in the endpoints. And what we're talking about today is integrals that are undefined someplace, either at one of their endpoints or between their endpoints. Remember, you can't plug in infinity as a number, so don't leave it up in the endpoint if your integral goes straight to the limit on it. Or if you are plugging it into answers at the end, don't plug in infinity. You can give an arrow and say goes to infinity, but don't treat infinity as a number. It is not a number. Okay, so let's talk about this one. Integral from -1 to 2 dx over x cubed. If you were just looking at the integral, I'm going to do this the wrong way over here. If you just go straight to the integral, this would be x to the -3 dx. What's the integral of x to the -3? Don't take a derivative. Add 1 to your exponent and you get -2 over -2. Goes from -1 to 2. Plug in your 2, and you're going to have a 2 to the -2 over a -2 minus plugging your -1. So you get 1/4 over a -2 minus -1 over a -2. Now, what's 1/4 divided by a -2? -1/8. And then -1/2. And that equals to some number. That's the wrong way. Let me get a red marker. Bright red. This is wrong. Now let me show you why. I mean, to all outward appearances, it looks correct, right? I haven't made a mistake that you can see. Except I would submit to you that you can't plug in 0 into the function 1 over x cubed. 1 over x cubed is undefined at 0. That means that what I have to do for the integral is I have to break it up at 0. And I have to take the integral from -1 to 0 and add to it the integral from 0 to 2. And then we have to check and see what's happening. Our function, if you look at the function 1 over x cubed, as you go to 0, goes to infinity, and minus infinity if you come from below. So I'm looking at some area here from -1 to 2. This is the area that we're looking at. It's probably an infinite area. In fact, it will be an infinite area. What we're going to do is evaluate each of these integrals separately. I'm going to evaluate the 0 to 2 one first. It doesn't matter which one I do. What I'm going to do is pass to the limit because I know that the integral is undefined at 0. I know the function inside the integral is undefined at 0. So I'm going to go straight to the limit. And then let's integrate that. We have the limit as a goes to 0, x to the -2 over -2 from a to 2, which is the limit as a goes to 0. Plug in our 2, we get 2 to the -2 over a -2 minus a to the -2 over a -2. Well, let's simplify. The 2 to the -2 is 1/4, so I get that 1/8 for the first one. In fact, it's a -1/8. And then the two minus signs here are going to cancel and give me a plus. Limit as a goes to 0, and I'm going to write this a 1 over 2a squared. Take that down into the denominator. What happens as a goes to 0? Where does it go? What does the whole thing go to? 1 over tiny is infinity. So this whole thing goes to infinity. So what happens to that integral? It diverges. Diverges to infinity. Now, if we evaluate the other one, we'll get that it diverges, but we'll get a minus infinity out of it because the whole area is below the x-axis. That's going to be a negative area. Infinity minus infinity doesn't equal 0. In this case, it still diverges. Okay? It still diverges. As soon as you get to one of these integrals diverging, you can't add them together to cancel your infinities. It just doesn't work that way. So you get diverges. The integral diverges. And you don't have to do the other one. Now, you will have one of these on the test. Don't make that mistake. If I give you endpoints to plug in on the test, more than likely it's undefined in the middle and your integral is going to diverge. Question?
So if we find that it's not continuous, we have to write all that out?
You have to do the integral because sometimes it will converge. So you actually have to evaluate it. If it doesn't blow up very fast, then it will be a convergent integral. And I haven't defined what very fast is. So yeah, we do have to evaluate it. Any other questions on that? Question?
So, like, if we were just to look at this on the test, how would we determine that we need to do the limit of?
You know that's undefined at 0. 0 is in between those two endpoints.
Just because we know that it's undefined somewhere in there?
If I had given you something from 1 to, say, 12, say, now you know you can integrate away, you're fine. But you have to break it on any place where it's undefined in the interval.
So if we have to, like, how to break it up, we have to see something. Otherwise,
Yeah. Any other questions on that? Okay. Let's look at another one. Determine whether the integral converges or diverges and evaluate the integral if it converges. So we have dx over the cube root of x. Where is 1 over the cube root of x undefined? Yeah. Notice that that is already one of my endpoints. So I'm just going to pass straight to the limit. So the integral is equal to the limit as a goes to 0, the integral a to 1. I'm going to write this as x to the minus 1/3 dx. How do we integrate x to the minus 1/3? Now you're taking a derivative. Add 1 to the exponent. What's 1 plus negative 1/3? 2/3. Divide by your new exponent. So you get 3/2. And then that goes from a to 1. So passing your limit, you're going to have 3/2, 1 to the 2/3, minus 3/2 a to the 2/3. 1 to the 2/3 is what? 1 times 3/2, 3/2. And then what happens to your a as a goes to 0? Goes to 0. So this part here goes to 0. So 3/2 times 0 is 0. So I get 3/2. Does my integral converge or diverge? Converges. Converges to 3/2. You can't tell if it's going to converge or diverge ahead of time. You have to integrate it first. And if you get a number for an answer, then it converges. If you get infinity for an answer or infinity minus infinity for an answer, it diverges. Okay? Any questions on that? Okay. You guys get to try one. Your first step is to determine where this is undefined at. One more, or that good? One to the negative what? Still one? Yep. I don't know why I have to be but it's negative one, the negative one power. That's still negative one.
Five by zero. I think by zero.
It's one over. you're maybe only. Right, okay, okay, okay.
I would agree that you, I don't know why.
Yeah, but then if you, so like you're only picking about it's complicated, but you don't get. After, this week, what she did there, she would care about. From second one to zero, it's not way.
No, why was that?
Yeah, but because if you don't add it, the reason why she subtracted. She got that why. Look, it's still
Yeah, what did you say now?
I just did one number now. So notice I started with the dx over x of 0 to 2, and I found it diverged. We don't even have to do the other one. You only have to do one of them. It's usually it diverges for each for one of them. There's nothing you can add.
Question.
So you don't have to do it. Diverges. It all has to be different variables. You don't need
Yeah, so it should be easy Yeah. So, A is 1.
Oh wait,
So, some of them.
so this is the A. This part is this right?
So, if this part,
This one is this.
so when you find this,
In theory, so.
this one, see it. Well, the power.
So I see right there. Okay, so what's okay, I get it. And when is it?
What do you have?
Okay, so it's infinity is. Does zero count as a number?
Zero is a number, one over zero is not.
Okay, like so if I got like zero, if I ever get the one of these, for my answers,
You can get zero
Like, so
for
that's-
areas that means that their kids have got the same negative areas as positive areas.
Okay, so that in those kinds of versions.
Yeah. Okay, guys, did it converge or diverge? Diverges. Yes. Think everybody is done with that one now? So, well, let me catch up on my slides. We're done with that one. Let's look at the arc length formula. We want to find the circumference of a circle. So our formula for a circle, this is our unit circle, is centered at the origin. The radius is 1. If I solve this equation for y, I get y as the square root of 1 minus x squared. Are we good with that? And that is our circle, like right here in our first quadrant. If I go from 0 to 1 and then multiply it by 4, I'll get the arc length all the way around the circle. So what is our arc length formula? I know I taught it to you guys. One plus y prime squared dx. So let's go ahead and take our derivative. What is y prime? First of all, let's rewrite y. It'll be easier. Write it with a numeric exponent. It's going to be to the 1/2 power. So what's y prime? 1/2 negative 1/2 times negative 2x. The 2 and the 1/2 are going to cancel, and you get y prime is equal to minus 1 over 1 minus x squared. Oh, that looks like a... There we go. To the 1/2. Took the negative 1/2 out, took that down into the denominator. Oh yes, we need the x. So now square y prime. What happens when you square the minus sign out in front? Positive. And when you square that x in the numerator, that's going to bother me. I want more space there. We get x squared. And what happens when you square the square root in the denominator? It goes away. You get 1 minus x squared. Now let's add our 1 plus y prime squared. And that becomes 1 plus x squared over 1 minus x squared. Get your common denominator. You get 1 minus x squared plus x squared over 1 minus x squared. Are we good with that? Tell me about the x squareds in the numerator. They're going to cancel, right? And I get a 1 over 1 minus x squared. That's my 1 plus y prime squared. So my arc length integral is going to be 4 times integral from 0 to 1. Those are the x values right here. Of the square root of 1 over 1 minus x squared dx. I would submit to you that's the same thing as 4 times integral 0 to 1. 1 over the square root 1 minus x squared dx. Where's my function undefined at? At 1. So that means I have to pass to the limit as a goes to 1, integral 0 to a, 1 over the square root 1 minus x squared dx. How do we integrate that? Yeah, I just want to say sub. U substitution doesn't work because if you make u be 1 minus x squared, you use a minus 2x and you don't have an x in your numerator. We had a different term that we also apply with substitution, trig substitution. If we use trig substitution, x becomes sine theta, dx is equal to cosine theta d theta, and the square root of 1 minus x squared becomes the square root of 1 minus sine squared. What is 1 minus sine squared theta? Cosine squared. And what's the square root of cosine squared theta? Cosine theta. So we get 4 times the limit as a goes to 1. I'm going to leave off the endpoints here because we're going to back substitute in a minute. And I get 1 over cosine theta, and my dx is cosine theta d theta. Does anything cancel? Yeah, the cosine thetas. And I have the integral of d theta. What's the integral of d theta? Yeah, it's going to be theta. 4 times the limit as a goes to 1 of theta. Now we have to make our triangle. Here's theta. X is equal to sine theta, so that's the same as an x over 1. So sine, is that opposite or adjacent? Opposite. So we get x, 1 minus x squared. There's our triangle. What is our theta going to be equal to then? Notice I didn't need my triangle. I could read it straight from x equals sine theta. What is theta equal to? Arc sine of x. And now that goes from 0 to a. Plug in our limits. I'm going to put a parentheses around here. Minus arc sine of 0. What is arc sine of 0? 0. And as a goes to 1, what is arc sine of a? What is arc sine of 1? Pi over 2. Because on your unit circle, sine goes with y, and so that's at 1. So this is pi over 2. So then that means we have 4 times pi over 2 minus 0, which is 4 times pi over 2. That becomes 2 pi. You guys ever wonder where your circumference of a circle comes from? No? Well, now you know anyway. Sorry. Question? Oh, no. Okay. Are there any questions on that? You guys seeing the process of these now? Pretty much. Plug in where it's undefined to take the limit. This next one's called Gabriel's horn. And it's mathematician's version of sarcasm. But it's actually true, what I'm going to show you, this information. But the reason they call it Gabriel's horn is it's named after the archangel Gabriel. And this is his infinite horn. What we do is we look at the line f of x equals to 1 over x, the function f of x equals 1 over x. And if you look at that function from 1 to infinity and revolve it around your x-axis, it sort of has a horn shape. You can kind of think of it, the angel standing over here. That's the mouth of the horn. It's a long ways that direction. This is an infinitely long horn. What we're going to do is we're going to find the volume in the surface area of this horn. Let's do the volume first. I just wrote a for all symbol instead of a volume. Volume equals, if I'm revolving this about the x-axis, I would submit to you that the Washer method is the easiest one. The Washer method is pi r squared, so we're going to have pi integral from 1 to infinity, and our r is the distance off the axis of revolution to the curve, so that's given by our function 1 over x, so I get 1 over x squared dx. Here we have infinity in the end point. So like we learned on Friday, we have to pass to the limit here. I'm going to write it as x to the minus 2 dx. How do you integrate x to the minus 2? Negative 1 over x, right? And that goes from 1 to a. Plug in our a. negative 1 over a minus negative 1 over 1. As a goes to infinity, what happens to our negative 1 over a? It goes to 0. And what happens to our negative of a negative 1? Positive 1. So you get pi times 1, which just gives you pi. The volume of Gabriel's horn is pi. Infinite horn, finite volume. Now, let's look at the surface area. The surface area formula was 2 pi integral from a to b, the radius square root 1 plus y prime squared dx. That's our surface area. The radius is the distance from the function, the axis of revolution, to the function. So in this case, our radius is going to be our 1 over x term again. It's going to be the same radius. And I have my function y equals to 1 over x, so I can plug that in. What is y prime? If y equals 1 over x, what is y prime? No, you're integrating now.
1 over x squared.
Yeah, negative 1 over x squared. Y prime squared is 1 over x to the 4th. And now I can plug it in. We get 2 pi integral from 1 to infinity, 1 over x square root 1 plus 1 over x to the 4th dx. Do I have an infinity in one of my endpoints? Yes. So I have to pass to the limit before we can evaluate it. We're going to have the limit as a goes to infinity, 2 pi integral from 1 to a, 1 over x, 1 plus 1 over x to the 4th dx. Now, tell me about this value underneath the square root. Is that value ever smaller than 1? 1 plus a positive amount. Is that going to be smaller than 1 or bigger than 1? Bigger than 1. So when you take the square root, is that bigger than 1 or smaller than 1? Bigger than 1. Square root of 1 is 1. Anything bigger than 1 will be bigger than 1 in the square root. So this whole part right here is greater than or equal to 1. Integrals follow that inequality, so I'm going to put a greater than or equal to sign right here, and then I'm just going to plug in a 1 for that square root part. Now, let's take our integral. What's the integral of 1 over x? ln of x. It's positive, so I don't have to pass to an absolute value. And that goes from 1 to a. Let me get more paper. Scroll it up a little bit. So this becomes the limit as a goes to infinity, 2 pi natural log of a minus the natural log of 1. What is the natural log of 1? 0. And what happens to the natural log as a goes to infinity? It goes to infinity. So then that becomes infinite. This diverges. Because it just, your integrals follow the same pattern as your numbers. So if you have an integral of a larger value and an integral of a smaller value, if this function is bigger than this one, the sum of the area under that function is bigger than the area under this function. Integrals follow the inequality. In other words, if you have the integral of a and you have the integral of b, and you know a is greater than or equal to b, then you know the integral of a has to be greater than or equal to b. It follows that inequality, which is why I can just ignore it. What this is telling you is that this original arc length integral is bigger than infinity. But what's bigger than infinity? Infinity, yeah. So you have an infinite amount. Now, what's very fascinating about this is, what was the volume again? Finite or infinite? Finite. Finite volume. Infinite surface area. You cannot paint Gabriel's horn with the paint that you can contain inside Gabriel's horn. Let me say that again. You cannot paint Gabriel's horn with the paint that you can contain inside Gabriel's horn. Yeah, it's enough to blow your mind away. It is true. It is a property of infinities. Whenever you have something that's infinite, you can have this happen. Infinite surface area, finite volume, your extra credit for the test. What? Both of them.
Oh, you're using it before the test?
Yeah, before the test. Turn it in at the start of the test. Well, one hopes that you did it in your own handwriting, but yes. Yes. It will be posted on eClass. You'll be able to copy it down. It'll be up on eClass. You don't have to get it today in the next 2 minutes. I'll put it up on eClass as soon as we're done with class. So you can get it from there. But this is the extra credit for the test. Yep. Okay, we are done for today. Make sure your names are on your papers and that you turn your papers in.